I'm making this video essentially to take you on a little mini tour of the operating system that I've developed over the past few months and show you some of the features and some of the basic functionality. So the core functionality of the shell is a read, evaluate, print loop. It's utilizing the UART2 serial port from the K70 to get and send its data. And it has support for standard in, standard out, and standard error. The shell does support quotation marks and escape characters, which is nice if you want to echo some random stuff in your terminal. We have all sorts of available commands. The core commands include everything that is listed here. Some commands that I implemented in addition to the core commands include fgetS and fputS, which are for getting and putting strings, respectively. Seek, which positions the cursor at a particular location in a file, in the FAT32 file system, which we'll talk about later. And malfree, which is a testing function for mallocing and freeing random-sized chunks of memory 100 times, just as a way of kind of stress testing the malloc and free functions. You can set the date and time in the shell by entering a value either in milliseconds or as a simplified ISO 8601 date-time string. I also added a function to my shell that it automatically acquires the current date and time at compile time. So we'll see what compile time was for this particular compilation. And there you go, in Greenwich Mean Time. That's what we get. So moving on to the device layer. Supported a range of different devices, including UART, FAT32, the LCD, which I described before, analog to digital, which includes potentiometers, thermistors, and digital and analog, the DAC, which I'll talk more about later. Also touch sensors, LEDs, and timers, including flex timer, PDB continuous, PDB one-shot timer, and the SysTick timer, which is used for multiprocessing. The OS does support FAT32 File System via the K70's built-in SDHC card. My implementation supports file names up to 11 characters, including just one directory, the root directory. Did add a few extra features, though. My LS does support extended directory listings, just like that. So you get file size, attributes like hidden or volume ID, and you also get to find out if a particular entry has a long file name that's not being displayed by my operating system, or that's being truncated by my operating system. The OS also supports date and time last modified, created, and append mode for writing onto the end of files, appending to the end of files. One other thing that I did that I found useful when debugging is I implemented a feature that allows the user to say the user is trying to open a file that only has 4 characters in its name, like Mars, and 3 spaces at the end. The user can input Mars period extension or Mars space 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 period extension, and it'll behave the same way. And that's just so I didn't always have to be worrying about exactly how many spaces I was supposed to type at the end of a given file, because, who really wants to think about that? All right, on to multitasking. The way the processes are scheduled is via a round-robin scheduler. The round-robin scheduler is triggered via SysTick interrupt, which sends us into the scheduler, and then the scheduler gets information from the PCB that it needs, and the PCB has a store of information that the scheduler needs in order to correctly save and restore the state of a process, including if it's in a supervisor call. So that brings us to the final project. A little Star Wars reference just to round us out here. The first feature I added was support for the TWR LCD RGB. So my operating system supports basic console I/O over the TWR LCD RGB, including echoing back the characters that are input over UART. Most of the functionality for this obviously is part of the provided materials, but the integration of it into the operating system took a little bit of work, as well as the allocation of the frame buffer. So in order to do its displaying behavior, the LCD RGB needs to reserve a certain amount of memory. And so I modified my malloc function to set aside the necessary amount of memory when it first runs. And that way it's always available for the display. The second and more involved feature was a synthesizer, which I created using the DAC. So I have a little bit of a video here that I'm going to show you. So here we have a demo of the synth. You'll see here that it is running in the terminal, and the leads coming from ground and from DAC 0 are going right into this oscilloscope here. Do not currently have it connected to a speaker. And the oscilloscope will fire when I hit the correct key. So here you'll see me pressing C. And here's A. Notice that A and the frequency 440 are in that neighborhood. Note that we can also change the waveform here. So if I hit W, we'll get a different waveform. There's a square wave. Characteristic, really more of a pulse width modulator. Really more of a PWM wave, honestly. So a few more details on how the synth was actually created and how all of this was implemented. So when the user calls the synth, there's some validation that happens at the shell level to make sure that the formatting of the arguments are correct and things like that. And then it's passed down to the I/O layer. At the I/O layer, the DAC is initialized. And the DAC is initialized in such a way that it has a 16-step buffer. And so this 16-step buffer, each of the steps in the buffer has a different level of voltage relative to the reference voltage that it is designed to send out. And that those different relative levels create the shape of the waveform. In other words, they represent the amplitude or the strength of the electrical signal. And the sweeping of the PDB, which is in continuous mode, it sweeps over that waveform repeatedly, or just as a one-shot, until the user either cancels it or until the release envelope completes. So there's a release envelope which is timed, and the amplitude slowly fades out until it reduces to nothing. And so then you can get notes of different lengths that way. So here's the synth playing with continuous PDB. From solid to square, or PWM. Here are a few little fun statistics for me from this class. As of the 9th, I had 336 commits on GitHub. In my repo, I had little over 7,500 lines of code in my operating system, 35 shell commands, and 18 devices. So quite a lot of stuff going on there.